Hello everyone and welcome to Lecture 12 of our Probability Theory course. Today we continue our exploration of the law of large numbers and limit theorems. These theorems are the crown jewels of probability theory and form the mathematical foundation of all statistical inference. We'll deepen our understanding and see how these results connect to real-world applications. Here's our plan for today. We'll start with a quick review of why we need limit theorems, then revisit the law of large numbers with a more formal understanding. We'll go through Chebyshev's inequality again, proving Chebyshev's theorem, the weak law of large numbers. We'll cover Bernoulli's theorem as a special case, then focus on the central limit theorem in detail, including the De Moivre-Laplace theorem. We'll finish with applications and a comprehensive summary. Let's begin with a quick review of why we need limit theorems. What happens when we repeat an experiment many times? If you toss a coin 10 times, the number of heads might be 3, 5, or 80. It's quite variable and unpredictable. But if you toss a coin 1,000 times, the number of heads will be very close to 500. The frequency of an event stabilizes around its probability. This is the fundamental insight behind probability theory. Limit theorems answer three important questions. First, does the average of many observations stabilize? Second, what is the distribution of the sum of many random variables? And third, how accurate are our estimates? These questions are essential for understanding how probability connects to the real world. There are two most important theorems in probability and statistics. First, the law of large numbers, which tells us that averages stabilize as we collect more data. Second, the central limit theorem, which tells us that sums of many random variables become normally distributed, regardless of the original distribution. These two theorems together justify why statistical methods work and why we can make reliable predictions from data. Now let's formalize the law of large numbers. The simple idea is that as the number of trials increases, the sample average converges to the expected value. Formally, let x1 through xn be independent random variables with the same mean and mu. The sample average converges in probability to mu. There are actually two versions of this theorem. The weak law of large numbers, which we'll focus on today, states convergence in probability. The strong law of large numbers states almost sure convergence, which is a stronger form of convergence. The key insight is that randomness averages out over many trials. The more data we collect, the closer our sample average gets to the true population mean. This is why large samples are so valuable in statistics. Before we prove the law of large numbers, we need to revisit Chebyshev's inequality. This is named after the Russian mathematician Pafnuty Chebyshev, who lived from 1821 to 1894. The inequality states that for any random variable with finite mean and mu and variance sigma squared, the probability that x deviates from its mean by more than epsilon is at most sigma squared over epsilon squared. Equivalently, the probability that x deviates by less than epsilon is at least 1 minus sigma squared over epsilon squared. This is a remarkable result because it works for any distribution as long as we know the variance. It shows that large deviations from the mean are unlikely, and it allows us to bound probabilities using only the mean and variance. We don't need to know the full distribution to make probabilistic statements about deviations from the mean. Let's look at a concrete example to see how Chebyshev's inequality works in practice. Suppose x has mean 10 and variance 4. We want to find the probability that x deviates from the mean by more than 3. Using Chebyshev's inequality, we get that this probability is at most 4 divided by 9, which is approximately 0.444. Equivalently, the probability that x is within 3 units of the mean is at least 1 minus 4 over 9, which is 5 over 9, approximately 0.556 or 55.6%. This means that at least 55.6% of values fall within 3 units of the mean. Remember, this is a weak bound und the actual probability is usually much higher. Chebyshev's inequality gives us a conservative guarantee that works for any distribution. Now we can use Chebyshev's inequality to prove the weak law of large numbers, also known as Chebyshev's theorem. The theorem states that for independent random variables with the same mean mu and finite variance sigma squared, the probability that the sample average differs from the true mean by more than epsilon goes to 0 as n goes to infinity. In other words, The sample average converges in probability to the true mean. The proof uses Chebyshev's inequality applied to the sample average. The variance of the sample average is sigma squared divided by n, so the bound becomes sigma squared divided by n times epsilon squared, which approaches 0 as n grows. This is a powerful result. With enough data, we can estimate the true mean with arbitrary accuracy. The probability of a large error becomes vanishingly small. A special case of the law of large numbers is Bernoulli's theorem. This applies when we have independent Bernoulli trials. Each trial is a success or failure with probability p. Let m be the number of successes in n trials. Bernoulli's theorem states that the relative frequency m over n converges to p as n goes to infinity. In words, the relative frequency of successes converges to the probability of success. This theorem provides the rigorous justification that probability equals long-run relative frequency. This is the foundation of the frequentist interpretation of probability. It means that if we toss a coin enough times, the proportion of heads will be very close to 0.5. This is why we can use empirical frequencies to estimate probabilities. Now we come to the most important theorem in probability and statistics, the central limit theorem, or CLT. The theorem states that if we take independent random variables with the same distribution, mean mu and finite variance sigma squared, then the standardized sum converges to a standard normal distribution as n goes to infinity. In words, the sum of a large number of independent random variables is approximately normally distributed, regardless of the original distribution. This is an astonishing result. It explains why the normal distribution appears everywhere in nature and statistics. Whether we're adding measurements, errors, or any other quantities, the result tends to be normal. This theorem is the reason why we use normal-based methods for hypothesis testing, confidence intervals, and many other statistical procedures. It's truly the cornerstone of modern statistics. For practical purposes, the central limit theorem tells us that for large n, typically n greater than or equal to 30, the sample average is approximately normal with mean mu and variance sigma squared over n. Equivalently, the sum is approximately normal with mean n times mu and variance n times sigma squared. What does this mean in practice? First, averages are approximately normal, regardless of the original distribution. Second, sums are approximately normal. Third, this works for any original distribution. It doesn't matter if the data comes from a uniform, exponential, or any other distribution. Fourth, only two things matter: the mean mu and the variance sigma squared. This theorem was first proved by Laplace and later generalized by Lyapunov. It's the foundation of much of modern statistics. A special case of the central limit theorem is the de Moivre-Laplace theorem, which applies specifically to the binomial distribution. It states that if x has a binomial distribution with parameters n and p, then for large n, the standardized binomial variable is approximately standard normal. In other words, the binomial distribution can be approximated by the normal distribution for large n. The rule of thumb is to use this approximation when n is at least 30, and both n times p and n times q are at least 5. This approximation is very useful because calculating binomial probabilities for large n can be computationally intensive. The normal approximation provides a much simpler way to compute probabilities. This was the first central limit theorem ever discovered by Abraham de Moivre in 1733, and it was later refined by Pierre-Simon Laplace. The central limit theorem has countless applications across many fields. In quality control, it's used to monitor production processes and determine if defects are within acceptable limits. In polling and surveys, it's used to estimate population proportions and calculate margins of error. In finance, it models stock returns and assesses portfolio risk. In medicine, it's used to analyze clinical trial data and compare treatment effects. In insurance, it helps calculate premiums based on risk and model claim frequencies. In physics, it models measurement errors and analyzes experimental data. The CLT is truly the foundation of many statistical methods and is essential for anyone working with data. It allows us to make inferences about populations from samples with known accuracy. Let me provide a comprehensive summary of everything we've learned today, along with practical applications that show why these theorems matter in the real world. We covered 5 key concepts that form the mathematical foundation of modern statistics. First, the law of large numbers. This theorem tells us that as the sample size grows, the sample average converges to the true mean, and the relative frequency of successes converges to the probability of success. In practice, this is why insurance companies can predict claims accurately. They have millions of policyholders, so the average claim amount stabilizes around the expected value. This is also why pollsters can predict election outcomes with samples of just a few thousand people. The law of large numbers assures us that larger samples give more accurate estimates. Second, Chebyshev's inequality. This is a powerful tool that bounds the probability of deviations from the mean using only the variance. It works for any distribution. We don't need to know the shape of the distribution. In practice, this is used in finance to set risk limits. For example, if a portfolio has a certain mean return and variance, Chebyshev's inequality tells us the maximum probability of extreme losses, regardless of how returns are distributed. It's also used in quality control to set tolerance limits without assuming a specific distribution. Third, Chebyshev's theorem, also known as the weak law of large numbers. This theorem proves that averages converge in probability. In practice, this justifies the use of sample means to estimate population means. Whenever you see a survey result like 60% of voters support candidate A with a margin of error of plus or minus 3%, you're seeing the law of large numbers in action. The theorem guarantees that with enough data, our estimates become reliable. Fourth, the central limit theorem, the most important theorem in all of statistics. It states that sums of independent variables converge to a normal distribution regardless of the original distribution. This is why the normal distribution appears everywhere. In practice, this is what allows us to use to test confidence intervals and hypothesis testing. When a pharmaceutical company tests a new drug, they use the CLT to determine if the treatment effect is statistically significant. When a factory monitors product quality, they use the CLT to set control limits. When a financial analyst calculates value at risk, they rely on the CLT to model portfolio returns. The CLT is truly the workhorse of modern data analysis. Fifth, the de Moivre-Laplace theorem, the special case for the binomial distribution, allowing approximation by the normal distribution. In practice, this is used whenever we need to calculate binomial probabilities for large samples. For example, in election forecasting, instead of computing complex binomial probabilities for millions of voters, pollsters use the normal approximation. In quality control, when inspecting thousands of items, they use the normal approximation to determine if defect rates are acceptable. In clinical trials, they use it to compare success rates between treatment and control groups. The key takeaway from today's lecture is this: with enough data, randomness disappears and reliable patterns emerge. While individual observations may be unpredictable, averages and sums become highly predictable. This is why we can trust statistical methods. This is why sample surveys work. This is why clinical trials can determine if a drug is effective. This is why quality control can ensure product consistency. These theorems justify why we can use sample data to make inferences about entire populations. The law of large numbers assures us that our estimates will converge to the true values. The central limit theorem assures us that we can use the normal distribution to quantify the uncertainty in our estimates. Together, they form the mathematical foundation of modern statistical inference. As you continue your studies, remember these fundamental results. They are not just abstract mathematical theorems. They are the reason why data analysis works in practice. They are the backbone of the entire field of statistics, and understanding them is essential for anyone working with data. That concludes our lecture. Thank you for your attention.